We have arrived at the last day of presentations, and I want to congratulate everyone who did the presentations, the last two sessions. Everything went really well. I really loved the demonstrations, and hopefully the discussion helped you guys understand some of the practical aspects of robotics. So this is really nice that we have a good discussion with among ourselves, and also some practical aspects about how tools are, how robots work, and what's a good way to do applications, which is the whole idea behind these final projects. So today we have three groups who will be presenting. So hopefully we'll be done sooner than 9:30 today. um, Everyone will have roughly 20 minutes time slot. Try to make sure that you keep a eye on the time as you're presenting. Take about 15 minutes to present. Start with the demonstration, your title of the final project, and all the group members then introduce themselves, and then first show the demo video. So we all see what you have done, and then start the presentation. We'll reserve 5 minutes for question and answers, and all your classmates can ask, I can ask, and guests can also ask. So before we start, if any of the guests wants to introduce themselves, please go ahead now.
My name is James Wallace. I am a graduate of OU in the spring semester of 2019. I had Dr. Mirza for this same class that you guys are in, and I am a senior project engineer at ABB.
Welcome, James, and good to see you.
Good to see you too.
Hi, I'm Deborah Kiefer. I work for the School of Engineering and Computer Science, and I always look forward to these presentations to see all the great work that you do. So I'm looking forward to it.
Welcome back, Deborah. And hopefully others will join you as we continue. Make sure you guys have your profiles set on the LinkedIn, and once all these presentations are over, we will put the videos on LinkedIn. So, and with tagging your name, so anybody who is interested in your project, what you did, can directly reach you. I see a new person, an old face. You want to introduce yourself, Sam?
Hi, Dr. Mirza, how are you? And Deborah too. My name is Sam Angeluni. I'm a creative director, graduate of CCS, and a longtime friend of Dr. Mirza. I've watched these presentations, over the years, and they've been great. They've been getting better and better. Unfortunately, tonight I can't stay too long, but I did want to come in and say hello and just give my support to you students.
Great to see you, Sam, and welcome. And
thank you.
And guys, you will get comments on your creative side also. He's a really good creative person here. Anyway, so we are ready to start, and we'll start with group number 9. KUKA writes home. Take it away, group 9.
Hi, everybody. So my name is Justin, and this is the group 9 video for KUKA Robot Writes Home.
Can you everybody introduce themselves before you start? Yeah.
Oh, sure.
Joseph Tituskin.
I'm Carson Crile.
You have Sachin Patil and myself.
Oh, and All right,
Okay.
so we're Group 9. That is our project, KUKA Robot Writes Home. I'm Joe Tituskin, like I said.
And I'm Carson Crile.
I'm Sachin Patil. Hello, everyone.
And Justin Hadyniak. So what is our project about in the big picture? Clearly, we're not trying to advertise this as a program that could do anything necessarily useful, or as a product, but instead we're rather demonstrating the precision automation and the integration of modern cutting-edge robotics with a traditional, more vintage mechanical device. So this program is using the KUKA bot to write a letter home cleverly to its parents. So the scope of work for this project, so the main task was integrating the KUKA robot arm with the standard typewriter through the use of an automated program, and ensuring precise alignment and control for accurate typing of each individual character on the typewriter keypad. So as far as the actual letter content, the letter that was typed out, the actual letter says, "Hi, Mom and Dad, I miss you. I hope you are doing well. I got a job in a plant and the hours are long." Sort of trying to make a reference to the classic repetitive nonstop role that robots typically play in our automotive manufacturing operations. As for the deliverables of this project, we needed a functional KUKA robot program that was capable of writing a letter on a typewriter and creating the video and now presentation of the program writing a sample letter on the typewriter. So as far as the actual timeline for this project, we had 5 separate phases, being the setup, the teaching and the programming, the testing and calibration of all the individual points, the demo recording, and then the documentation, including the presentation and final report. So for the setup, it was really just the workspace prep, making sure that we had datums in the robot cell that we could use to accurately mount the typewriter and to install the robot tool repeatedly. The teaching and programming consisted of the key mapping, so being able to establish a local point in the robot cell to teach the hover and key press positions for every alphanumeric character on the keypad, and then sample testing to be able to make sure that the test keys were only pressing a single key and that the sort of translation of the key was enough to make the key stamp have good pressure on the paper. And that was also part of the testing, so controlling the test to make sure that the speed was appropriate for the ink roll. And then creating the video, setting up the camera angles, making sure the lighting was good, recording the video, and then combining everything together. Are we stuck here?
Okay, so components and setup. So we have 4 main components: KUKA robot, workstation, typewriter, and the tool. I want to talk a little bit more about tool because tool selection is very important here. For typewriter, it's very critical. Force is a critical, means force should be appropriate in order to type it properly. Too low force is not going to type, it doesn't type properly on the paper, it doesn't print properly. Too high force, it causes the skidding effect of the tool on the surface of the keys. So that's what we choose the tool material as a steel instead of lightweight like plastic or wood. And why we choose the steel? Because it's for its durability, strength, and because steel doesn't deform easily, so it has the ability to consistently transfer force directly on the keys. So that's very important. And another thing is that the concave shape of the tool is matching with the curvature of the keys. That makes sure that reliable contact with keys. And then we choose the dimension in such a way that it's not too heavy. Setup, we mount the typewriter on the workstation, load the paper manually. We attach the tool securely in gripper, and we run the dry motion to check the clearance and the reach. Next slide, please. Typewriter mechanics, typewriter is completely mechanical without electronic component. It has, each key has the lever, that lever connected with another key which is called type hammer, and each type hammer lever has a slug of metal type at the end of it. So just as the type about to hit the page, the ink ribbon lift and sandwich between the paper and the type, and that way type make the printed impression on the paper. Once we release the hammer type, then it will fall back up to its original position. Workflow, secure a typewriter. So we secure the typewriter on the workstation. Good thing about typewriter is self-weight. So it's very stable because of its self-weight. So we don't have to add any other clamping, additional clamping on it. Align the typewriter. So on the workstation, it's very important to align and position the typewriter. So we use two metal blocks on the workstation which are exactly perpendicular to each other. So we position the typewriter across, we use those as a datum, and then we position those typewriter across these two blocks which are already there on the workstation. We mount the tool on the gripper and we test accessibility. So we check whether robot move the complex position across the typewriter. Then we keep position back mapping, manually moving the robot. We did the program keystroke movement test. We test individual keystrokes. We complete the typing and we test it for accuracy and readability. And that's the end of workflow. Now for next section, I'm handovering to Joseph. Thank you.
I'm going to give a run through and explain our robot's program sequence. So firstly, the robot moves to its assigned local home position. Next, an individual sequence for each key consisting of a hover position as well as a button press is programmed so that it can return back to that hover position before it goes to the next letter. Each sequence or each sentence that was shown in the video was programmed individually, both to allow for error correction and in order to monitor mechanical key displacement during testing. And because the entire program ended up being something over like 300 lines of code. So after the desired sentence was typed on the keyboard, the robot would then turn to home position. You can go to the next slide. Oh, that's it. Speaking on that prior mentioned strategy of having the hover position, each keystroke has a programmed hover position above the designated key by a height of about 15 millimeters above the key. This position is used twice in the programming of each letter. So where the actual press of the key is sandwiched in between that key's hover position. So it's hover, letter, and then another hover. And then you can go to the next slide again. So this was done for a couple of reasons. Most importantly, this process ensured that the tool didn't hit or slide against any of the keys as it moved from point to point on a horizontal plane. We originally had it so that it would type one key and then return back to home position and then type on another key. The problem with that is that it then moves diagonally. So it would drag itself across an entire row of keys to try and hit the next one. And that happened because the vertical location of the key, when you press it down, it's then lower than the key that's next to it. So it ends up snagging on it. So it fixed this issue. And then on top of this, it simplified our programming paths, at least from point to point, because we only had to program one separate point that was directly underneath the original one that we had programmed.
All right, so now we're going to the conversion table we made. So to be able to be flexible with message typing, it is important to be able to quickly translate message characters to keystroke positions. That has been done via a lookup table that will convert any message into its corresponding robot positions. So basically, we made this table in order to track each of our key positions for the letters. So whenever we tried to type in, like here, it says, "Hi, Mom," you see that we have each designated hover key, hover position in order to easily track each of the letters. So it made it a lot easier when trying to actually, like when we were coming up actually with what we're going to write. It made it a lot easier with tracking, like being organized with that and actually going about seeing how we would do that. So next slide. challenges. So keys dragging when using PTP movement method without an intermediate step somewhere else in the vicinity. So as was previously mentioned, this intermediate step was very key, because if we just go right from a press, go up and then like right to another key, there's going to be a lot of dragage, and there's going to run the keys, and it could risk damaging the typewriter. So that press hover position was very important, and knowing how high that hover position had to be was also very key, because that dragage can occur very, very easily. Typing text requires a lot of characters, and spacebars adds additional points. So yeah, as was also stated, it took over 300 lines to make this, and the spacebars, as they were needed to actually make the letter readable, it did make it a little bit more tedious. But the speed with which the keys are pressed dictates how well and even if the letters come through on the letter paper due to the age of the typewriter and the ink ribbon. So this typewriter is over 100 years old, and the thing is you have to get the speed to be pretty like decently fast in order to get a good output on the paper for the thing to press and hit the paper. So we had to make sure that the speed was fast enough and it goes down enough, or in order for there to actually be something to print onto the paper. So doing that at a good medium was important. Additional mechanical issues in the form of the typewriter keys / hammers getting stuck or displaced. So actually this kind of goes into the previous point. So like, in getting the amount of force and distance into the key press, even though like it would cause the thing to actually be pressed into the paper, this presented issues with stuckage happening, where like, for example, a letter A that we had some problems with, whenever we pressed it in, it tended to be stuck for a little bit, and we had to get around that and try to make the letter so that wouldn't present an issue. But again, that would still tend to happen. Type precision needed on keystrokes due to the translation of the keys on the hinge path, and and the tight spacing between keys. So this is very important because the robot is moving really fast, and we need precision, because we wanted the pointer we chose was a wider and heavier sort of pointer, because getting each key press into the letters had to be relatively strong, because this typewriter requires a lot of like hard presses. It's not like a normal computer. So these tight precision strokes had to go through, we had to go and make sure that they were perfectly in line to make sure that it didn't cause overlapping and press A and S or G and H at the same time. So next slide. Potential improvements: automated paper loading system for typewriter, so you could it would keep typing and then automatically another paper would slide in, keep going. Use camera or sensor to confirm each character is printed. That would have been nice, to make sure that the hammer actually strikes the paper and you can actually see an output. Add logic for detecting stuck keys or missing keystrokes and attempt automatic correction. Yeah, that's pretty straightforward. Multi-tip quick change system. So this would be nice for if you wanted to use this, but not just for a typewriter, but also for a normal computer. And this would be good for like even just like normal laptop, because the key, you don't have to press into it super hard, but you want to use this program, but now you want to have like a soft tipped pointer. So you could switch to a softer tip pointer and you could still use the program. User-friendly key mapping interface instead of hard coding, just easier for finding the keys. Auto-adjustable hover height mechanism. So if the hover height isn't correct, it can adjust on the fly. Adaptable force feedback mechanism. That's basically tracking the force going into it and knowing the force needed to properly get the right keystrokes on the paper. And ink ribbon consumption tracker, so just keeping track of your ink when you're typing. And next slide, and that about wraps it up.
Yeah, thanks everyone. Are there any questions?
Good job, group number 9. Can you unshare the screen?
Yeah, I have a question. I was going to ask, why use a typewriter as opposed to a computer or a laptop, but I think I understand. I think you made it more challenging for yourselves. And I really like the storytelling. I think this could be a Black Mirror episode on Netflix, actually, if you're familiar with that show. I thought that was a very, very good presentation and good exexecution too.
Thank
Good
you.
job.
Thank you.
Thank you.
I
But
agree with
why did you choose a 100-year-old typewriter as opposed to a laptop?
I can say that we can preserve the authenticity of mechanical typewriter while adding the robotic precision. I can say that. So that's what we choose the typewriter.
Well, I like your choice.
it ended up being very nostalgic looking video. You should have done it in black and white. But I was thinking that once robots have AI, they might really be writing this in reality, these type of messages
Yes.
to their moms and dads.
Well, good
Well,
job. I like to echo Sam's comment about the storytelling. I thought that was really clever with the mom and dad robot and their child robot working in the factory. I had a question about, and maybe I just missed it. Like, how did you do the capital letters? Because did you have to push a button before the letter just to turn it to a cap? How did that work?
So all of our keys that we pressed in the actual program were lowercase. We
Okay.
had an additional button for the shift key, but it was very tedious just in trying to keep it 100% grammatically correct because it adds another 3 lines. We especially had problems towards the end when, since it was so many lines long, it would slow to a crawl, so it would be like impossible to program it. So we just ended up keeping it lowercase.
Okay, that's good. And then my other question was, did it give you an appreciation for people of the past who actually had to use that typewriter?
Yeah.
Definitely.
Yeah,
It was
well,
like 45 pounds.
yeah. It was
Heavy.
very heavy. It was very heavy, but also I think it gave me an appreciation of the people that designed it because it's like magic to me, the way they got all those functions to work.
That's
Mhm.
true too. And I hate to say this, but I think I can remember using one because my grandmother had one that was very similar to that. All right, well,
Yeah.
good job. Good job, guys.
Thank you.
Thank you.
I wanted to make one comment that we didn't talk about it in class, like actual industrial robot programming. So you guys figured out that the hover point is usually called an approach point. So when you're doing anything precision, then you first come to an approach point and do a precision move to do what you want, mostly a linear move at that point. You can come to approach point in P2P or joint motion quickly and then precise motion. So you guys did the right way to do that. So thumbs up for that. More questions?
I know you guys had said that you thought it was sort of a basic task for a robot to perform, but in doing the project that you did, you learned a lot of like techniques that we have to focus on in the actual industry, like having speed controlled applications, and tool design is one of the most important things. So I think that you got very, very good experience from doing this project. Good job.
Thank you.
Thank you.
Yep, I agree there also. One question. So in designing of the tool, did you figure out that you needed any kind of compliance? Like you chose steel as the tool to press the key. What was the reasoning behind that? I mean, do you feel that a tool with some kind of compliance would have done a better job or a worse job?
For
Probably a worse job just based off the key translation. So it follows a nonlinear path as you press it. We tried a couple other tools, but we were running into issues where the tool was actually slipping in the gripper. So we had to add some sort of, I think that was actually our biggest issue, was that the previous tools we tried to use were slipping. So we needed something that was fixed in the gripper, but also rigid.
Yeah, so
Okay.
for typewriter application, it's very important to transfer the complete force consistently on the keys. So and the steel is the have the property like is less deformed compared to other material. So that's what we use basically steel, which is just for typewriter. If we go for like, for example, any other apply like stylus, right? If we touch screen, so we can use the tool with spring actuated tip on it at the end. So that way, or maybe silicone pad on it. So we can, but for typewriter application, this tool, steel tool is important. That's what we come up.
Because you had to press it with some force
Right.
to actually type. There must be compliance in the key itself, because whenever you have a application of force using a robot, you should always think about compliance, because heart to heart contact is never good when you're using a robot. So I think your keys had the compliance, which made that tool doesn't need to have any compliance. So yeah, we talked about in our previous sessions also, like how important compliance is if you're trying to apply constant pressure without any force feedback. So you kind of use the tool to do all that stuff. I do have one more question here. Calibration. So you calibrated by placing the typewriter in a fixed position, teaching it, and then you always put the typewriter in that. I was thinking that you could use another method here. Like you can go to, let's say, one corner of the keyboard with, let's see what, the Z key. So you hover over the Z key and position the typewriter so that it's over Z. Then you go to the other extreme, let's say a P key, and you make sure the orientation is right and you are calibrated. So that means that you can always, even if your blocks are gone, you have two points on the typewriter which you are locating and you're placing your. So that's another way you could do a quick calibration anywhere. And where if you don't, you're not relying on, if you lose those block positions, oh no, how should I place my typewriter now? That's another way to do it. For simpler application, not very precise ones, of course, without vision or without other feedback. All right. Any other comments from anybody else or questions? All right, good job, Group 9.
Thank you.
Thank you.
Okay, we're gonna move on to group number 10, who are going to present SketchBot. Take it away.
Okay. Can you guys see my screen? Okay, yeah. 1 second. I think I shared with the sound. Okay. All right. So hello everyone. My name is Ryan Younes.
And I'm Ani Xhaxho.
And I'm Joey Georges.
And this is our project, SketchBot. So hello, this is our project, SketchBot. It is a robotic system designed to autonomously create drawings with precision. Our objective was to create a robot capable of translating some sort of digital images or patterns into physical sketches using pen-based actuation and the ABB IRB 120 robot. And so if you're not artistically talented like I am, you might find this cool to use because then it allows you to actually start drawing. Our initial approach was to use the Robot Studio program to create and upload rapid code. Rapid code is the code that the ABB robots use to move. The reason why we wanted to use Robot Studio is that it allows us to create paths for like more intricate pictures or 3D models rather. One of the most useful tools that it offers is the AutoPath tool. So using 3D objects, such as the grizzly bear that I've shown on the bottom pictures, you can trace the edges of that object, and you can create a path out of it. And you can control the zoning, and you can control the velocity of that path. In our example, this was a 3D step file that we used. And so using the Robot Studio from the ABB company itself, we're able to create some paths. And so as you can see on the simulation results on the right, the robot is able to trace the outer edge of the grizzly while keeping its configuration stable. I should mention that the Robot Studio itself has multiple models, and you can also attach different tools to the robot to the end frame itself. The picture on the left shows the generated code for this for this one particular path on the outer edge. So you can see it's about 28 points just for that one outer path, and it has a bunch of, I can control all the velocities and the zoning on it. I should mention that although this did work in our simulation in a virtual controller setting, when we had a bunch of problems when trying to upload it to the actual robot in lab. We connected to it with an Ethernet cable. We're able to upload the code. Trying to launch the code, we had to go through a lot of hoops, some of which the TA was able to help us with. When we ran it, we would encounter a lot of issues with singularities, which we were somewhat able to mitigate by changing where the path is actually located physically to somewhere else on the workspace. However, as the robot was following that path that we gave it, it was flipping in orientation a lot, even though the simulation results indicated that it would be stable. We think this is most likely due to us not calibrating it correctly with the tool frame, which we were not quite sure how to do. And we had to make a decision, which was for us to essentially scrap all of this idea of using Robot Studio to trace the actual object that we want to trace. And Ryan will talk about it on what we did after we scrapped it.
So obviously we had to act quickly because we were running out of time. And so the OU logo came to the rescue. We wanted to stay in the theme of Oakland University, so not very far from the Grizzly. We ended up using the Oakland University logo. We decided on that because first of all, it was the same as it was very, it was still in the same theme, but it was also not very complicated when it came to the form of it. We had to change from the Grizzly because it was very complicated and it required a lot of inputs into our robot. So the two main functions that were used to draw our Oakland University logo was the move L and the move C. So the move L is the linear movement and the move C is the circular movement. The move L only requires 1 point in the code, which just tells the robot to what point it wants to move. And it will just take a linear path to that point. Whereas the move C requires 2 points. The second point being our end, the end of the circular motion, and the first point determining whether our circular motion is going to be in a clockwise or a counterclockwise way. So if we put it to the left side, then it would be clockwise. If we put it to the right side, then it would be counterclockwise direction. We also ended up adding the invisible marker to just as a fun thing at the end to also showcase the precision of our robot. At first we wanted to do that using the robot as well, but unfortunately our marker was not spring loaded, and so we were running into a lot of applied pressure issues with the robot, and sometimes it would just lift off of the paper slightly and it wouldn't apply enough pressure. Sometimes it would even just apply a bit too much pressure and just rip the paper apart. So we ended up deciding on just tracing where the OU logo would be based off of previous run we've had. And obviously it shows that it was pretty accurate and pretty consistent in the drawing of the logo. Here is a simple flow chart of the paths the robots took. So the robot was placed at an idle position at the beginning, and from that idle position we use a move L to move to the starting point on the paper so that the pen is touching the paper, and from that we use different combinations of move C's and move L's to draw our OU logo accordingly. And at the end, once we were done with our OU logo, we made sure to have our pen lifted off and placed into the same idle position again. And that was pretty much it for the flow of our robot. And now I'll give it to Joey so that he can talk about the 3D print.
So yeah, with our project, we decided to use a custom end effector for our robot. So using the power of the internet, we were able to find a custom design for the ABB120 robot that fit our project needs. So initially, we were brainstorming of how we wanted to do this. Did we want to use a software like SolidWorks and create a 3D model and then machine it using machining tools? Did we want to design our own 3D printable object and then print it off? Or did we just want to save time and go on the internet and find something that will fit our needs to print and use? So we decided to go with the latter. So why did we go with a custom end effector? Well, we wanted to have a firm grip on the writing utensil so it would eliminate any sort of stuttering or inconsistencies. We also wanted to eliminate any of the aspects of the pressure inconsistencies. As you can tell with the picture on the right, there's a spring in the middle. So when you would press down with an extra amount of pressure, the spring would compress and it would absorb the pressure. And as you drag, it would keep that consistent. We also wanted it to be more challenging. We didn't want to just use the robot gripper. So we decided to utilize the use of an end effector to add a little bit more challenge and a little more pizzazz to the project. So that came with some challenges. So what were some of those challenges? Was, like I said, finding a design we like. We also had to find a way to construct this custom design. The project we found was a 3D printable mold. So we used 3D printing with plastic to 3D print the end effector and fit it to the robot. So then we would have to fit the design to the robot. The design we found was specifically designed for the ABB 120 robot, so you could easily attach it. Then we would have to actually test the design with some trial runs. So after we fitted the end effector to the robot, we came up with some sample code, drawing to some lines, some semicircles, all that stuff to actually see how it would act and react to different commands. And then finally, obviously, it was utilizing the design to complete the project. And that absolutely came with no issues. As you can tell, it flowed like the Titanic that we decided to include. Just kidding, just like the Titanic, it crashed and burned. Thankfully, nobody drowned at the end of our project. So the first issue we ran into was attaching the end effector to the robot. The end effector that is currently attached to the robot is a hydraulic controlled robot gripper. So to remove it, you would have to remove the hydraulic lines that are attached to the robot and reassemble it after we were done. We didn't know how to do that, so we decided not to execute upon that because we couldn't put it back together, and we didn't want to affect future users of the robot or mess up the robot in any way. The second issue we ran into was that our end effector actually broke while we were coming up with our design and actually executing it. This stem part of the robot you could see in the picture actually snapped when we applied too much pressure. In hindsight, we should have used better material, but we only decided to make one object, and it was a soft plastic, and it ended up breaking. So the third issue was actually figuring out how to fix it and execute it. Well, thankfully, we ended up MacGyvering the situation using a hot glue gun and some tape to actually reattach it and finish executing the project. So in conclusion, what was the point of all this? For the group as students, we wanted to test our knowledge of robotics so far by applying our knowledge throughout the course, as well as expand upon that by using things outside of the box. So for example, we knew how to code a robot, but we didn't know how to use the software that we decided to use, or use a custom end effector. So we also wanted to put existing ideas to the test. As we have all learned through the course, robots are really good at doing the same thing, but what challenges actually come with that? If you execute the same code multiple times and iterate upon it, what issues would you run into? What issues would come up with using code? What issues would come up with using end effectors? So that was another thing we wanted to put to the test, and some food for thought. After executing the project, we encountered challenges that may affect others that in broader industries using these robots. So the closest industry we can talk about is the car industry, who use these robots for what, 24 hours a day, 6 days a week. There's many different kinds of these robots, spot welders, grippers. They are all executing the same code over and over. Well, what if you wanted to change up what you were making? You came up with a new design, how easy it is to change it. Is it easier to use the actual pad, or is it easier to use code? If you wanted to change the end effector because it wasn't working as intended for longevity, how would you do that? What material you could change? And what can you do to avoid these issues? And how can you improve the process by cutting down the time and also creating more product? Thank you.
Thank you for listening. Thank you for your attention, and we'll take any questions.
All right, group number 10, good job. Can you unshare your screen?
Yes.
All right. So did you add the TM part to the logo, or OU will come after you? Trademark.
Well, you might come after us.
Okay. I have to say that you guys went extra mile there. Kudos for using Robot Studio and simulation on your own to just try out and see how that software works with it. I wish you had also, it had worked out, but we have an expert here, James. He would explain maybe why you run into some of those issues, singularity stuff, and what's the right way to do it. So we'll open up for questions.
I would just like to say, never underestimate the power of hot glue and tape.
Yeah, in hindsight, we should have maybe printed more than one, knowing that it could have broke, but that's 2020, and we had to do what we had to do at the moment.
Yeah, I did like with the OU, the invisible ink, that was on the paper before we saw the actual tracing, right? So then that was demonstrating how accurate. I got that. Okay,
Yep.
that was clever.
Thank you. We used the previous trials that we had to just place under the paper that we had, and so we could see in the general area where the paper, like where the drawing would be, where the logo would be, and we just filled it out, just as a nice twist to the end.
Good job.
Yep.
Nicely done.
Thank you.
That was a good touch, a good surprise ending there. And again, you could have used 2 points on it to calibrate the paper, a calibration routine that you make your robot go to 1 point of the drawing and the diagonally opposite maybe to just position the paper properly. That's a good way to do it.
Yeah.
So James, you want to say some comments about Robot Studio and singularity handling? I
Yeah,
think they would benefit from it.
the singularity is one of the biggest things that you deal with in the industry. One of the best ways to avoid it is unfortunately mostly out of your control. The best way to avoid it is just cell design, where you place your robot, how you mount your tooling, but you guys are limited, obviously, like you said, you don't want to disassemble the tools off of that robot and you can't change the mount. So you guys did great with what you had. But when that's a very similar application to what you guys did in the industry is dispensing. So that's taking, I've done epoxy, I've done RTV, and you can take whatever path you want and you import it and generate a program through Robot Studio. So it's very, very applicable, everything that you guys did.
Yeah. You want to ask him about why it split? Thank you.
Thank you.
With your calibration of your tooling.
Yeah, do you we're just guessing that the calibration was the issue that led to the robot just turn up or turn in ways we didn't want it to, but we're not even sure if that is the point. But do you have any idea if that is the case or if there's anything else?
So there's a hole pattern on the end of those robots that if you were to build an actual tool, let's say there's 4 bolts, there's one dowel that indexes the tool so it can only go on one way. However you set up your tool in your TCP in the model could have been skewed off. And also whatever the direction is, like your plus Z coming out of your tool center point could also have something to do with it.
Okay, thank you. Thank you.
Yep.
So I'm sure given enough time, you would have figured out all that stuff. It's just, and James knows that a very limited time, about 4 weeks to do everything, come up with an idea and actually make the tool and implement it, and then run into Titanic issues also, and then try to steer around it. So I understand that. But you guys forgot one thing. I told you not to modify the tool. So there was no chance for you to remove the gripper to mount the other gripper. That's one of the rules which we have in the robot lab, that you can't change the gripper because somebody else is going to work right after you. So we can't mess up. Yeah. Other questions for the group? Any of the classmates or anyone has a question? Feel free.
I have a question about your guys' curved lines. You guys mentioned that to do the circular motions on the ABB robot, you picked 2 points, a starting point, and if it goes clockwise or counterclockwise. How do you pick how big the radius of the circle you're going to draw is?
So, do you want to answer?
So the 2 points that you choose, essentially, your first point doesn't just choose the direction, but it's also a point that lies on that circle. So you're essentially choosing 2 points that lie on a circle, and your second point is the end point on that circular path. So if your end point is further away, that means that your radius of your circular path is also large. The way we typically did it is we let our first point be halfway in the semicircle, and the third point be the last point in that semicircle.
Okay.
Yes, to clarify, Andrew, it's 3 point. You need 3 points to do the circle, not 2.
I figured as much, yeah.
Yeah.
I do believe it is 2 points. The initial point is basically where the robot is, and then you just place 2 extra points. So it just takes automatically your initial point, and then the first point you place on the code is just the basically the second point, the halfway through of the semicircle, and the third point is our second point we put in in the code as well, and that would be the final one.
So you only pick 2 points,
I
but
agree,
there's
right?
kind of 3.
Yeah, we are saying the same thing.
Okay, yeah.
Points are on the circle.
Yeah.
Your first one is where you start the circle, you're already there. So that's 1 point. And 2 more makes the 3 point to know where to get the arc to go through.
Yes.
So the algorithm knows that. So yeah, you're right. More questions for group number 10? Any last questions?
Overall, I thought you guys had an amazing presentation. Thank you. I did want to know though, if you were to use some sort of computer vision, do you think you could have done an edge detector or some sort of like edge filter to place the points automatically rather than having to put them all yourself?
I suppose you could especially if you don't know the object that you're going to be working with. If it's some kind of application where it's not a object, you can just pop into the Robot Studio program and just say, hey, trace the edges of this object that you already have. I suppose machine vision would be what you do to trace the edges.
Thank you.
One of our previous groups actually used a webcam to take an image and then convert a line image to convert it to a program, Robot Studio program. And they actually used the SCARA robot because that's you're not going to run into the singularity issues with the other robot. It can just sketch it on it very quickly. Yeah.
That would be cool for a collab.
Yeah, exactly. Yeah. Any other questions? Great, good job, group 10. Okay, and
Thank
we
you.
have finally come to the last group. Yes, it's sad times. But we'll have the group 11 who is gonna talk about ABB, another ABB project, ABBstract Stacker. So take it away, group 11.
All right. Hang on. There we go. All right. Can everybody see well? All right. So we're group 11. Our idea was the ABBstract stacker. I'm Austin Nieporte.
Nolan Nowak.
I'm Joey Osterhoff.
And I'm Dale Szydlowski.
All right, and then I'm gonna start it off with the video. Let me know. Should be good. Okay, yeah. All right. That was the video. I think I'm gonna pass it on to Nolan now. Oh, all right.
All right, so just a little brief introduction to what the project was about. We used the ABB robots given to us by the class to stack 6 of these relative solo cups, one of which I have right here, up into a pyramid pattern of 3 by 2, and then 1 on the top. In order to ensure the robot could over and over again pick up the cups, we used a cardboard to kind of mark our area, where just take a little Sharpie, mark around the cup, and mark a little tick as well as where our peg would go to ensure that the robot could pick it up every time. And then we'd finally use a pencil to just add a little bit of precision and show how precise we can get in between the cracks of the cups themselves. So some very early limitations we found out regarding the gripper was the size of the standard gripper itself. It's pretty small in terms of actually having to pick up the cups. So gripper is about this big when it's fully widened, and obviously the cup size is much bigger than that. So can't do much for actually turning it up, picking up. So some early things we were trying to figure out, as most groups were, is did we want to have a little attachment on the side of the gripper to pick it up? But something that kind of led us to not using that was another problem was that originally we wanted all the cups to be stacked on top of each other at the beginning and then pick them up one by one. But we had a problem where the friction itself of the cups were, if we tried to pick up one, half the stack would move with it. So in doing with that, we decided to use these little wooden pegs, just take a big thing of dowels and cut them up and attach them to this in order to actually be able to pick it up and move it to where we go. However, that of course added another problem with our original plan of having them all stacked together, as having these dowels meant that the cup would lean to multiple sides. So for the terms of actually being able to do this over and over again efficiently, it means that every time we'd stack it, these would be leaning a little bit away and be hard for the gripper, as small as it was, to effectively actually be able to pick them up. So unfortunately, we had to move to actually having all the cups unstacked to begin with, and then we'd put them in the pyramid form and then move them all together rather than being stacked themselves.
So this is a simple flowchart of how our code is structured. I want to point out that in this flowchart, there's no decision symbols. Rather, it's all process boxes. This is because the robot never actually really makes a decision. Rather, it's hard-coded in, and it just executes the command in a specific order. So to start off in the loop, similar to group 10, we use many of the move out commands. This is just a linear move from one point to another. And then anytime we want to use the gripper to make it open and close, we had to use a set do gripper command, either 0 or 1, depending on what we wanted it to do. And then we ran into an issue, which will be discussed later in the presentation. For whatever reason, the gripper was closing before it reached its desired point. The solution to this was including wait time commands. Basically just added a delay so the gripper closed when it was supposed to. And then the last part of the loop was stacking the cup on the top of the tower. Up to this point, it was all very repetitive, a lot of the same movements. And then getting to the pencil, once again, more move out commands. Set do gripper command to pick it up, and then more move out commands to kind of stick the pencil between the gaps, and eventually pushing the cups down and stacking them. And then after this occurs, the program is ended, and the end effector will actually go back to its home position. So if we had more cups off to the side, we could reload them, put them in their home positions, and it would keep going.
So some of the issues that we've come across when programming robots, like Joey has mentioned, the gripper kind of activating at the wrong time, closing too early before it's around the dowel, so it crushes the cup, or opening too early, so it drops it like halfway through its movement. Not to mention, we've also had some technical difficulties with the robot, and for some reason, at time when we kind of came back, our code was gone. I'm not sure if it was another group or just some other, or just whatever technical difficulties the robot had. But the main ways that we kind of solved these issues well, you can move to the next slide. Thank you. But the way we solve some of these issues, we used the wait time command originally. Well, we did end up using it at the end to help solve our early drops. I would rather have used something that would have kind of said like when it was at this position, so we could have actually changed the speed on it. I don't think that time command would actually allow for like the change the speed on it. And we had used a largely iterative process of just constantly moving to the cup, going down and grabbing it, similar to group 9's wait, action, wait, or kind of like hold, action, hold kind of process to grab the cup and then move it. Though in some of our cases, we could actually move the cup beforehand without having that additional weight. Honestly, I would have liked to at least having a place offsite, well, off the robot that I could actually store the code on. And I'll pass it on to whoever's next for, I believe it was Joey for improvements, right?
Yep. Yeah, so if we were to do this project again, or we had more time, there's several different improvements we'd try to make. Firstly, creating a wider gripper to pick up the cups. As Nolan mentioned, the width of that gripper was around 15 millimeters. And obviously the diameter of the top of the cup is much bigger than that. So maybe creating some sort of custom gripper where it could actually pick up the cup itself instead of needing a dowel. And then optimizing path planning for faster execution. So if we were going for speed and kind of wanted this to move quickly, we'd be very specific in where we put our move L positions. For example, at the end of that video, when it raised the pencil over the tower, it went kind of high over the tower. If we wanted to speed this up, we'd make sure that pencil was barely missing that cup, and we could get it moving much quicker. And then implementing some sort of machine vision system into this project. So what happened was when we set the cups at their home position, it always kind of fluctuated by a couple millimeters in any direction. So if we had some sort of machine vision software that could actually see the cup, it could be a lot more consistent in picking it up. And then lastly is modifying the part in which the gripper picked up the cups. As mentioned earlier, we use a little wooden dowel, and an issue that would happen is that we go to pick it up and the cup kind of tilts on its side. So maybe 3D printing some uniform part we could put across all the cups could be a much more consistent grab.
All right. Thank you, Joey. Just to introduce practical applications for the robot. So for us, we were trying to show the precision and repeatability of the robot. So when we would stick the pencil in between the cups, we would be showing the precision. And then the repeatability, obviously we've had issues, but our main goal was to be able to stack the cups and then put them back into kind of all stacked on top of each other. But since we had the dowels, we weren't able to actually do this. But if we had the correct parts and maybe a change gripper, we would have been able to do that and then show the repeatability of this robot. And then in addition to this, the robot, we were trying to show that the robot can do tasks that are like menial for humans, which would save time for whoever would be working, let's say on an assembly line. You could implement a robot in place of a worker. And then real world applications, you'll see robots doing this kind of in any job field, really, from the automotive to even like the health industry. And majority in like industrial workplaces where it's a lot of like line movement, where it's picking up moving parts, even depending on the tool, assembly of parts as well, and just different use cases like that. So to wrap everything up, just going to talk about what we got out of the project, and what we were trying to show and our end goal. So first part of the project, we kind of had to learn and understand how we can control the robot, and see how we could use it to be used for, in our case, stacking cups. So with the gripper, obviously we had limitations, but overall, I think we kind of were able to put the cups in the spots we needed to. Unfortunately, we couldn't have the repeatability that we wanted. But maybe if we had a little bit more time, we could have been able to implement it. And then secondly, as all engineers could relate to this, would be the resiliency of working on a project when you're kind of hard stuck on a wall. Because there was a few times where we would go in to work on the project and the robot needed to be calibrated or recalibrated, and then we'd lose all our progress. In addition to creative thinking on how we would want to design the tool. As said before, it was probably one of the most important parts of the project. But if, like I said, if we had a little bit more time, maybe we could have had some kind of a different, instead of a wooden dowel, some kind of 3D printed structure, or if able to, we would have maybe changed the gripper on the robot, taken off the gripper, and then had maybe like these pneumatic suction cups to pick up the cups. And then for the goal for the project for you guys, our goal is to demonstrate the robot's ability to show repeatability of the different stacks for the cups, as well as accuracy and precision of our robot. And I think that sums it up. I think we're going to open it up to questions now.
Thank you, Group 11. Good job. Can you unshare the screen?
Yep.
Great. So I know we have severe speed limit restrictions in the lab, or you'll get a ticket, right? So you did your whole thing in slow motion. It looked slow.
Yeah,
but
I believe
that's
we
what
had the 20%, I believe we were at. So
right, right. So I understand that, but I think you had a nice touch with the pencil at the end to show the precision and doing the human-like, cup stacking move at the end. That was good.
yeah, the
Let's
video was a bit jittery, but it actually did it pretty cleanly. So
great. Okay, let's open up for questions.
I don't think I have a question, just a couple of comments. I mean, I could, just watching the video, I just definitely thought of construction industry and being used for construction purposes and stacking things that are really high for people to do physically, or replacing forklift operators maybe with more robotics where they can work, stacking in the warehouse type of use cases. But good job. Love the mic drop at the end. And congratulations.
Thank you.
Thank you.
Good comment, Deborah. Pick and place operation is one of the most important applications for robots. Many industries, that's what robots do, pick and play. Pick an object one, place at another point. Do it quickly, over and over, precisely, repeatedly. And that's what they earn their bread and butter for. Now, I have a question. So one of the most important things for precise pick and place is tool design. So how you design the tool so you can precisely pick up the object, precisely place it. In your case, what do you think would have been the best tool? I know that you didn't have the luxury to put any tool on it, but what would have been the best choice of tools for your application to pick up cups?
Yeah, I mean, if we could have changed the gripper of the robot, I actually had, I don't know if you guys can see it, but it's just like these small little suction cups that we could use the pneumatic tubes for. And then they have like a little give to them, so there's like a spring inside where you could press it onto the top of the cup. So there would be no interference of the dowel on top of the cup. It would just be the suction cup going on top of the cup, picking it up, releasing the pressure from the suction cup into the spot, and then continuing with the program.
Yes, and I totally agree. Suction cup, any size cup it doesn't matter. You just need a flat surface, smooth surface, so suction can work and it can precisely pick and release. So that would have worked pretty good in this scenario. If you try to hold anything which is, flexible like that plastic glass, you can't even apply too much pressure because you're going to crush it. if you use it like a mechanical way to hold it. And plus, as soon as you hold it, it just jiggles, right? So so you will lose precision right there. So I think you got the best compromise there with a little solid, piece there, so you can, reliably pick that, and if you and hope for that it's not wiggling too much after you grip her. And then if did you put any kind of rubber material at least on the dowel or in the gripper, so it can apply some nice even pressure and it will even be even more precise that way. So again, cool design here. So that would have might have improved your accuracy a little bit more there. So when it presses, it applies a force, which is, it just keeps that in one place. So one issue which you had with the gripper timing, James, you want to talk a little bit about it? Maybe they will learn how the gripper opening, closing, and in the program works.
Did you guys use your points after the the type of move, the position you're going to, and the speed? Do you remember what it said after that? Was it like Z1, Z10, or did it say fine?
I don't recall. Anybody else?
I don't remember.
Usually the default is Z10. So basically, if you have a point in space and you want to move to that point and continue to the one after that, the Z is something called a zone. So once it hits 10 millimeters of that point, it will round the corner and continue moving to your next point.
And since the drop command was kind of immediately after it, like it would move to within 10 millimeters, then trigger the drop command or whatever gripper command, and then move on to the next point.
Yep.
Yeah,
exactly. There's you can swap that to a fine command, which will purposely stop at that point before it continues.
Yeah, I was hoping that we could how that would be implemented in the robot, because if we could do that, we could just like turn up the speed and have it go essentially full speed without any error at that point. Because with wait time, it's going to wait like so many seconds, or however many seconds you program it, until like regardless of the speed. So if it says 5 seconds, then it's going to drop at 5 seconds, regardless of that 20 or 100% speed.
Yeah. If you're doing something like moving from one point in the air to another point in the air, that's when you want to have those zones, and you can make them pretty big. So that way, if you know that you're clear of everything else on your workspace, it can just round those corners and get to the end as fast as it can. But usually when we're finishing a path to do something, we always end in a fine point. So it's stopped before we close a gripper, we start turning a servo to tighten bolts or nuts or things like that. So that's one thing you guys can do. But as you guys learned fixturing, anything that you're picking or placing is very, very important. That anything that we have to do, as long as there's not machine vision, you obviously need to make sure that whatever you're picking up or putting down is always going in the same spot. So that's in industrial automation, that's a very big job for mechanical engineers, is figuring out how to locate your parts. But apparently I picked the good day because I got to see 2 ABB groups. So
yep.
Good choice.
And James, I do have an answer to your question. It said Z50 at the end. Is that too high?
Yeah, you need fine. So you're basically you're 2 inches away, and that's when it's firing the gripper.
Yeah, that sounds about right.
Yeah.
Excellent points. And if you guys remember when we were talking about trajectory planning, continuous move, that's what it is. That the points where you don't want to stop, you just plan a trajectory, it comes near it and then starts moving towards the next point. So it will never stop, it will have continuous velocity, and you're managing the acceleration moving to the next point. It's like, going in a bomber and you're under the point, you're just dropping a bomb there. So you're opening a gripper without stopping. So yeah, you have to time it. Like, when do you want to do that? So best way is to come to a stop at the point and then open close grippers at that point. So, but I'm not saying that the other approach is totally unacceptable. There are applications where I saw that it was so fast, pick and place with suction cups, that you have to really open or release the things before you reached it, so that the timing of the whole thing is that as soon as you reach, it's ready to fall. So you have applications where you have to kind of use the continuous moves and timing to open close to get it just right. But you guys kind of ran into it and learned a whole lot. Now you will never forget, like how to do these things. That's great that you did that. Any other questions for the group?
I have one question. So, can we, can we extend this if we have industrial application where objects are on the conveyor, or conveyor is moving and the objects are moving on the conveyor? Can we extend this pick and place?
Yes.
Yes.
You would
That's a
need some
good
machine vision or some sort of machine
Yeah.
vision to kind of deal with any variance within the conveyor. Not to mention, we didn't really clear our workspace in our program, so we kind of needed to do that as well. But counting those two factors, then you should be able to get something to work, right?
There are conveyor tracking applications, not so much in powertrain, but in paint, it's very, very important, where they'll put an encoder on whatever you're using for your transport, and it gets the exact speed that everything's moving, and it shifts the robot as it's moving, which is pretty cool. But it's really, really important for paint applications.
Yeah, in just one thought, in machining applications also, because there are steps machining processes for one component. So they go on the conveyor, let's say cylinder head, they go start after casting, they do first operation, and it done by robot pick it, put it on the CNC, do the operation, come back, take it back on the conveyor, it goes on next machine, robot pick that and put it on the machine. So there are in powertrain, because I have a little bit experience working in powertrain machining industry, so there are a lot of conveyor, and in assembly operations also a lot of conveyors there which robot picking and doing assemblies. So that's what I asked that question. So thank you. Yeah,
That's a good point, Sachin. And again, you could use machine vision if the parts are coming and you don't know how they're going to be presented to the robot. Then you need machine vision to actually locate the orientation of the part, position orientation. And what James was talking about is, if you put a position encoder on the conveyor, that you know the exact position of the conveyor and the parts are coming in a structured way, then you can get away without vision, because it's going to come exactly and the robot can track the conveyor also. Then you can use a combination of vision or precise just picking up. So multiple ways you could do the tracking for. We did that when we were talking about frames. We assigned the frames properly, and if you have a frame which is moving with the conveyor, you're planning a trajectory to a moving frame, so you will automatically track the conveyor.
Yeah,
as you
calibrate with respect to station frame, and then right that one. Yeah. Okay.
Okay.
Thank you.
Any last questions for the group? All right. Good job, group 11. So we have come to an end, and thank you very much for joining Deborah and James here. Any last comments for the students?
Just really, really impressed and enjoyed all the presentations. So congratulations to everybody.
Yep. Good job, everyone.
Thank you both. And I will be putting all these videos, demo videos on YouTube. The links will be, I'll send them shortly. The videos and the presentations all. So you can watch it in full glory. My sound was cutting out, and that's Zoom, but you will see in good quality all that stuff. And next Wednesday, we will meet one last time before the finals, and we'll go through the reviewing the entire course. All right, so with that, I want to say bye to everyone and have a great evening, great night, and we'll see you on Wednesday. Take care,
Thank you.
everyone.
Thank you.
Thank you.